Hello, everyone. My name is Paul, and welcome to BurkTech Leviton Technologies webinar. Today's topic is Enterprise Wireless Network Planning. Our roughly 55-minute presentation today will cover wireless demand planning and preparing for the long term, emerging wireless standard 802.11ax, and where 5G cellular fits in your network planning. Our presenters today are Yuna Shin, Senior Product Manager for Leviton's Copper Solutions, and Mike Good, Manager of Applications and Systems Labs at BurkTech. But we'll start today's presentation with Yuna. Yuna, take it away.
All right, thanks, Paul. Again, welcome everyone, and thanks for joining our webinar today. So today we have a lot of good information that we want to share about enterprise wireless options. So without further introduction, I'll get right into the presentation. So today's webinar focuses on gaining a better understanding on different enterprise wireless options that we currently have today and in the future. And we'll discuss which options will give us the highest return on investment. So we will be covering current and future options, including the emerging Wi-Fi 802.11ax and cellular 5G technologies. And we will conclude our webinar with our recommendation. So as we already know, there are so many wireless options that are out there. There are so many options and there are so many terms like 10 gigabits per second, Cat6a, 802.11, Wave 1 and Wave 2, and so on. And if you throw cellular into this mix, like 4G and 5G, it gets even more confusing. And some of these technologies and terms are interrelated and can be used interchangeably, but sometimes we do use this incorrectly. So as we go through this content today, I'll try to clarify what these all mean so we can reference them better in the future. So let's begin by looking at the wireless families first. So basically, there are two types of wireless families. We have a Wi-Fi family and we have a cellular family, and sometimes cellular is called mobile, but for consistency, we will refer it as a cellular for today's webinar. So Wi-Fi and cellular share a lot of similar technologies because they both use radio frequency to transmit signal. But what I'm going to focus on this slide is what the main differences are. So the first one is the standards body. They are specified by a different standards body. Wi-Fi is specified by IEEE, which stands for Institute of Electrical and Electronic Engineers, and cellular is specified by 3GPP, Third Generation Partnership Project. And because they are controlled by a different standards body, they have different names. The Wi-Fi standards are called 802.11 with some type of letters following after that. And cellular uses letter G with numbers in front of it. And you're probably more familiar with the cellular family names because of the cell phone. Now, they're both working on new wireless specifications. IEEE is working on 802.11ax, which I will explain shortly, and 3GPP is working on 5G, which Mike will cover in the second half of the webinar. So use of frequency is another difference. One of the most important elements in wireless transmission is frequency. And we'll talk more about frequency later today. But basically, Wi-Fi runs on unlicensed frequencies versus cellular runs on licensed frequency. So what this means is that for a cellular network, the government licenses these frequencies to service providers. So it requires paid subscriptions. That is why cellular services are much more expensive than Wi-Fi service. Now there is a discussion about 5G using unlicensed frequencies, but 5G cellular network for enterprise has not been well defined as of today. So we are going to stay with what we currently know. And lastly, there is an in-premise cabling requirement for Wi-Fi network. For example, if you currently have a device that is connected to a Wi-Fi network, that device is getting signal from a wireless access point installed somewhere in the building. And that wireless access point is wired to a switch through Ethernet cable such as Cat5e, Cat6, or Cat6a. On the other hand, cellular does not require in-premise cabling. So if you have a device that is connected to a cellular network, you're getting the wireless signal from cell towers around the location. And again, this is as of today for enterprise space. So these are basically the main differences between Wi-Fi and cellular, and what is the reason that these two families are so important? So let's take a look at some data. Now you can see how fast IP traffic is growing. This is the data from Cisco Visual Networking Index. Interestingly, wire connection has not decreased. In fact, it is still growing, as you can see in the purple bar. But a lot of them have been replaced by wireless networks. For example, in 2015, more than 50% of data was running on wire connection. In 2020, the wire connection will drop to 33% of the total IP traffic, and more than 65% of data will be expected to run on wireless, either on Wi-Fi, cellular, or both. So it is very evident that wireless has become so pervasive in our lives that it changes the way we communicate, it changes the way we work, and it changes the way we live. So that is why it is important to talk about and have a good understanding of these two wireless options. So I will start out by explaining the Wi-Fi options in the first half of the webinar, and Mike will cover 5G cellular in the second half of the presentation. So as I explained earlier, Wi-Fi is specified by IEEE. The very first Wi-Fi specification was released in 1997, and it has gone through 5 major advancements, and now we're at 5th generation of Wi-Fi. Now, most of you are probably used to seeing names like 802.11a, G, N, and AC, and so on. Recently, Wi-Fi Alliance, which was originally created by the members of IEEE, developed a new naming system to make Wi-Fi simpler to identify and easier to remember. So they started calling Wi-Fi 1, 2, 3, 4, 5. So the 5th generation of Wi-Fi, which is 802.11ac, can also be called Wi-Fi 5. Now, this is the chart showing different parameters for 802.11 specification. Now, I'm not going to go through all these numbers, but what I like to highlight here is that all of these numbers, the technologies and techniques are really to achieve this maximum throughput. Because at the end of the day, what really matters is the performance, right? How fast and reliable our network is. And as I mentioned already, there have been multiple rounds of development to ensure that our technologies meet the fast-growing demand. So let's briefly go through some of the important differences between these standards. The first, the speed is the main difference. Now, you can probably see by looking at these numbers that 802.11ac Wave 2 has the fastest speed. So as an example, 802.11ac can transfer a 5 gigabyte file size in 6 seconds versus Wave 1 takes about 33 seconds. So just going from 802.11ac Wave 1 to Wave 2, you are gaining about 80% faster speed of your network. So this can make a huge difference in workplace efficiency. So speed is the main and the most important improvement of these evolving technologies. So next one is the frequency. Now, as I mentioned earlier, frequency is very important in wireless because in wireless world, there has always been a trade-off between speed and range. And one of the main reasons is because of this frequency. So wireless signals can run on 2.4 and 5 gigahertz frequency. The 2.4 gigahertz has narrower bands, and it is currently used by many legacy and current devices such as cordless phones, microwaves, Bluetooth, and some of the older wireless access points. So it is very crowded, and it does not provide a very clean and fast signal. Now, on the other hand, the 5 gigahertz frequency has a wider band, and there are less devices using this frequency, so you can achieve faster, cleaner, and less interference signal. But the wavelength in 5 gigahertz frequency is much shorter than the wavelength in the 2.4 gigahertz frequency. The signal with the shorter wavelength means that it cannot easily pass through walls or obstacles. So it is more vulnerable to obstructions and more sensitive to obstacles. So you have to be closer to the transmitter to be able to get a good signal without a lot of interference. And this is the reason why higher frequencies can provide a higher speed but less coverage. So the big question here is, how can we achieve the speed and coverage at the same time? And this is where a good infrastructure design comes in play, which I will discuss later today. So before we talk about the design, let's take a look at the cabling requirements, and I believe this will make a very good transition to the design section. So the older devices such as 802.11n and G require Cat5 and Cat6 cabling and connectivity because the maximum speed that was required was 600 megabits per second. So Cat5e and Cat6 with 1000 base T supporting 1 gigabit per second were sufficient. For 802.11ac, the maximum speed is higher than 1 gigabit per second. Like for wave 1, it is 1.3, and for wave 2, it is 6.9. So we can no longer support this with Cat5e or Cat6 cabling. So we will need to use Cat6 cable with 10G base T that supports up to 10 gigabits per second. Now, do you start to see the relationship between all these terms here? At the very top row is the IEEE specifications. The second row, the megabits per second and gigabits per second designations are basically the speed of your network. So how fast these devices are designed to support. The gigahertz is the frequency that this technology is run on, which is one of the most important factors determining the speed and coverage. And the cabling infrastructure is designated with Cat5e, Cat6, or Cat6a. Now the base T is just a IEEE 802.3 physical layer specification for Cat5e, 6, and 6a infrastructure. So I know it gets a little bit confusing at first, but once you start seeing the relationship, it should be fairly simple to understand. All right, so let's get into the cabling structure. Now I'll show a larger image of this diagram, but basically the main difference between these two most commonly used designs are use of a circular pattern versus a uniform cell design. So let's take a look at some older wireless cable structure. Again, this is just an example of many designs that are out there, but this design closely resembles the design that was recommended by ISO, which is using the circular pattern. So basically, this design is from ISO IEC TR 24704, which is the technical report for customer premises cabling for wireless access points. This standard recommends placing a wireless access point in an array of tight-fitting hexagonal cells with no more than 12 meters in radius, with the outlets close to the center of the cell. The outlet location is usually the location of the access point in this case. So let me show this in a very simplified lifestyle image. Now you can see that there are 4 wireless access points placed in a hexagonal pattern, as you saw earlier. The one thing that you may note here is the direction of the signal. The older devices like 802.11n and G has a signal that is omnidirectional, which means it spits the signal everywhere in a circular motion, hoping to hit one of the wireless devices that are out there. Now, remember back in the days when we moved around with the wireless devices to find the best spot? This is the reason. Now, although this ISO recommendation is not specific to any Wi-Fi specifications, the combination of this design with the signal direction of older devices make this recommendation more suitable for older Wi-Fi networks such as 802.11n or lower. Now, on the other hand, TIA recommends a very specific way to design for newer Wi-Fi networks. TIA TSP 168, which is the telecommunications cabling guidelines for wireless access point, recommends using 18.3 meter uniform cell design as shown on the right of the screen. Now, this design gets really specific with the cable types and length. Basically, what it is saying is once you divide the space into these uniform cells, pull 2 Cat6 cables in each cell, and the length between the patch panel and the equipment outlet should be no more than 80 meters, and that is your permanent link. Again, patch panel to the equipment outlet here is the permanent link, and it cannot be more than 80 meters. Also, in the cell, the WAP core should be no more than 13 meters, and the maximum length of your equipment core in the telecommunications room is no more than 6 meters. So this entire length from the switch to the WAP is your channel. And this design will give you the highest chance to meet the theoretical speed that the specification is designed to support. Again, this is a simplified lifestyle image. Now you see that each cell gets two Cat6 cables, even if you're not using them all, right? So you can connect each cable to two different WAPs, or you can connect two cables to one WAP for a linked aggregation to boost speed, or you can just use one cable and leave the other cable unused for future use. So this is basically a future-proof design. Now, one thing that you may notice on this image is that the Wi-Fi signal is not circular like 802.11n. Now, this is because 802.11ac uses a technology called beamforming, which sends a concentrated signal by communicating to the client. So instead of broadcasting the signal all different directions, it finds exactly where to send the signal. So going back to the design, this is highly recommended design for 802.11ac wireless deployment. Now let's move on to the new standard. Now, so far we have talked about what is currently out there in the market, and some of you or most of you probably are familiar with a lot of them. This section focuses on the new specifications that was recently introduced or the ones that are expected to be ratified in the next year or so. So first, let's stay with the IEEE 802.11 specification. So there is a new standard in the works, which is called 802.11ax, or the sixth generation, or Wi-Fi 6. This specification is expected to be released sometime next year. So for today, we will not get into specific parameters. So what is the main driver for this continued development? Now, we know that things are changing so fast, and we're seeing a huge increase in network requirements. Bring your own device continues to grow. We're looking at a compound annual growth rate of 57% for mobile devices and almost 50% for tablet adoption in enterprise space. The voice over Wi-Fi is expected to grow 52.9% in 2020. So it is very clear that wireless has transformed from a nice to have to a must have. And we rely so heavily on wireless, and we expect faster speed, improved reliability, and overall increased efficiency. So what is the sixth generation of Wi-Fi, or 802.11ax? Now, but keep in mind that these specifications have not been released. So rather than getting specifics into the numbers, I will highlight the goal of this development and some major improvements from the previous generation. So there are three major goals for 802.11ax. The first one is supporting high density applications such as airports and stadiums. So one of the challenges that we face with Wi-Fi networks today is supporting high density environments. So through improved multiplexing and signal modulation techniques, the goal of 802.11ax is to support ultra high density environments and at the same time, increase the average client throughput speed by 4 times. And very importantly, it will improve power efficiency, especially for IoT applications. Now, unlike other wireless networks, IoT is connecting hundreds of devices, so it requires more intelligence in use of data and power. So there will be a new power saving mode technique called target wake time to negotiate the client to an access point for wake time schedules to conserve power, which will result in significant power savings for power devices, especially in the IoT applications. We are planning on having more detailed technical focus webinar once the specification is released. So hopefully we can have some quantifiable numbers for these measures next year. So again, the takeaway is 802.11ax allows Wi-Fi to service high-density applications such as airports, stadiums, and school. And this will meet growing needs for IoT, 4K, 8K videos, augmented and virtual reality applications as well. So let's quickly compare the 4 elements that we discussed earlier today with 802.11ax in the mix. So the preliminary speed target for 802.11ax is around 10 gigabits per second. Now, actually, we're looking at about 14 gigs. So we're expecting a minimum of 10 gigabits per second. So using the example we saw earlier, now we're looking at around 3 seconds to transfer a 5 gigabyte file. So again, huge improvement from the previous generation. Another thing that's going to change with 802.11ax is the frequency. Now they are going back to using both 2.4 and 5 gigahertz frequency to allow flexibilities for low data rates. Also, the plan is to improve coverage through implementation of a different multiplexing technique. So even though it is still running on 5 gigahertz frequency, you'll have the speed and coverage at the same time. So when it comes to cabling, it does not change much. Cat6a cabling is already supporting 10 gigabits per second. And with the link aggregation, you can double that speed. So supporting 10 gigabits per second with Cat6a should not be an issue. This is why it is very important to design your network with future expansion in mind. If you pull two Cat6 cables today, this will last for a long time and you will have higher net present value and can maximize your return on investment. So as far as the structure cabling goes, now this is the recommendation that you saw earlier. So how does the new structure look like with 802.11ax? Again, 802.11ax has not been released, so there is no formal recommendation specific to 802.11ax. However, there have been preliminary studies that the current TIA TSB 162.8 guidelines can use for 802.11 Wi-Fi deployment. So this tells you again how important it is to implement future-proof design, especially the physical infrastructure where it is relatively difficult to upgrade. Again, this is just highlighting different speed comparisons for 802.11 specifications. Now let's move on to non-802.11 Wi-Fi specification. Now what we discussed so far is IEEE 802.11 Wi-Fi specifications. The 2.5 and 5G base T, as name explains, it is a physical layer designation focusing on infrastructure cabling. Now when the name was first introduced, it got very confusing with 5G cellular. Remember, this is not a 5G cellular. Now it is specified to support up to 5 gigabits per second, but the clear way to say is 5G base T, and this is about Wi-Fi, not cellular. So both IEEE and TIA released the specifications to support 2.5 and 5G base T in 2016 and 2017. So let me briefly explain what this is. Now, it would be easier to understand if you actually see the graphics. So I will use this diagram throughout the section. So this is the current cabling structure for a Wi-Fi network requiring up to 1 gigabit per second. Now, you saw this diagram earlier today. Now, the increase in wireless demand has pushed the network capacity and the threshold beyond 1 gigabit per second that Cat5e or Cat6 can support. So the ideal solution is to support more than 1 gigabit per second is to upgrade the infrastructure and the device to support more than 1 gigabit per second. So you are upgrading cabling and connectivity to Cat6a, and you're also upgrading active gears to 10G base T and 802.11 AC wireless access point. So ideally, this is the design that we want to get to for wireless networks that need more than 1 gigabit per second. But this upgrade may not be feasible for all applications because there might be cost involved and it may be too high, and some older buildings may not have large enough cable pathway to accommodate larger cable size. So what active gear manufacturers has proposed as a temporary solution is all you need to do to gain a little faster speed is simply upgrade the switch to support 2.5 and 5 gigabits per second and upgrade the wireless access point to 802.11 AC. And you do not have to upgrade the cable or connectivity, and this still gives you a speed of more than 1 gigabits per second up to 5 gigabits per second. So basically, the cabling structure does not change or does not have to change if you want a temporary short-term solution to support up to 5 gigabits per second. But when it comes to 2.5G base T and 5G base T deployment, there are some elements that we must consider. As you know, alien crosstalk is not specified for 5G, for Cat5e or Cat6 cabling, so that must be considered. There may be some PoE support for concerns with some of these older cables that are installed that are out there. There may also be some distance limitation. Remember TSB 155? This could be a very, very similar situation. Also, very importantly, I talked about 802.11ax specification, which will support up to 10 gigabits per second. Since 2.5G base T and 5G base T can only support up to 5 gigabits per second, that's why we're calling this a very short-term solution. So you need to consider all of these factors and carefully decide whether this system will work or not. But if all the implementation is done correctly, this could be an effective short-term solution for a cost-sensitive project.
Thanks, Una. We'll transition now to Mike Good from BurkTech for the next part of our presentation. Mike, I'll go ahead and make you presenter.
All right. Thank you, Paul, and thank you again, everyone, for attending today. Even if you don't follow technology all that closely, you have probably already heard about the term 5G and thought, what is that? During this presentation, we will review what it is and how it may impact your network in the future. So what is it? Well, it's big for cellular networks. You may even hear people say some of the following things, such as 5G is a general purpose technology. It will be used in all aspects of society, including manufacturing, transportation, financial, agriculture, and residential applications. You also hear about its enormous impact that it will have on the infrastructure development for data centers, cellular towers, and even at the city level for city planning. And one other item that you might hear people talk to it or refer to it as a fulcrum for the Industrial Revolution 4.0. And this last one I particularly like because it really gets to the point that the 5G is really a tool that we'll use for this so-called Industrial Revolution 4.0. So before we can really get into what exactly is 5G, we need to talk a little bit about what is this fourth industrial revolution. So most people are probably familiar with the first industrial revolution that took place in the 1700s. And that was really the mechanization of the way we work. That was things like steam power and the weaving loom. There was still a person there, and they were pushing buttons or pulling levers, so it was really a force multiplier of how people worked. The second industrial revolution was mass production, like the assembly line, electrical energy. Most people probably think about this, they probably think about Henry Ford, the Model T, and the assembly line for building the cars. And the third industrial revolution was really about computers and electronics and the internet. So for the fourth industrial revolution, what we're talking about what we're calling cyber-physical systems. And these are simply systems that blur the line between the physical, digital, and the biological spheres. So some of the technologies that you'll see included in the so-called fourth industrial revolution are things like robotics, artificial intelligence, quantum computing, the Internet of Things, the industrial Internet of Things, 3D printing, and fully autonomous vehicles. And of course, last but not least is 5G, you see here on the list. And just to take a quick little sidebar here, I'd like to talk about the Internet itself for just a moment. And when you look on the right side of the screen there, you'll see that the Internet itself has had several different stages through its lifetime. In the first initial stage, the Internet was really used for people to communicate with other people and to collaborate with each other across long distances. The second stage is really about people communicating with machines or servers, and that's where we are today. A good example of this would be streaming a movie over Netflix or something like that. You know, it's one person or a couple people interacting with the server, getting the data that they need served to them. The third stage of the Internet is really going to be the machine to machine. And this is where we're going as a society. And this stage will be characterized really by machines interacting with other machines using data from sensors and probes to make decisions about what to do and when to do it without any interaction with people at all. So now that we kind of understand what the fourth industrial revolution is, or what we expect it to be, we can start to examine the characteristics of the 5G that will make some of these things possible. And the first thing that I want to talk about is millimeter waves. So these are simply signals whose wavelengths are on the order of a millimeter in length. So if you look at the distance between the crest of a wave to the next crest of the wave, it's on the order of about a millimeter. And if you talk about this from the perspective of frequency, these are signals that are in the 30 to 300 gigahertz range. And the reason that this characteristic is included in 5G is simply that the faster the frequency is, or the higher the number is on the frequency, the more bandwidth you have in the same amount of time. The second characteristic that I want to talk about are small cells. And if you think about most cell phone antennas today, you probably think about the large 300-foot towers that stick out from the landscape and are easily spotted. You know, even the ones that you see kind of designed to look like trees as you drive down the roadway, you know, you can still tell those are antennas for cell phones, all right? But with 5G and small cells, these miniature base stations will be put just about anywhere that they're needed. So this will be things like on utility poles, on the tops of bridges, on the sides of buildings. Some people are even talking about built into the infrastructure for the city, such as, you know, street side trash cans on public streets. All right, so the base stations will be ubiquitous in high density numbers, and they'll use a lower power than what the current antenna systems use today. The third characteristic is massive MIMO. And MIMO is simply multiple input, multiple output. And the base stations that will be deployed for 5G will potentially have hundreds of these antennas, which is a sharp increase over the existing antennas. And this will allow for many low power devices to be connected to the network in an efficient manner. The fourth part of 5G that we'll talk about is beamforming. And this is simply an intelligent way of choosing the path that data will reach the end device. And this will include knowingly bouncing the signals off of high buildings, off of other natural geographic features. And what this accomplishes is that it uses the available spectrum in a more efficient manner. The fifth characteristic that we'll talk about is full duplex. And this is simply the ability to send and receive data at the same time between a device and the antenna. And in the end, this really just ends up doubling the capacity of the physical level. So there's quite a bit of benefit to this. So here on the screen, I won't go through all of this, but this is a list of the cellular technologies that are found today. So you can see that today the data rate is approximately 150 megabits per second. The frequency is below 3 gigahertz. And the latency, which is simply the amount of time it takes for a device to send a request and receive a response, is a little over 50 milliseconds. If you look forward into LTE technologies, which stands for long-term evolution, there's multiple versions of that. So if we look at the versions 10, 11, and 12 that we expect to be adopted widely in 2020, the data rate has increased to 1 gigabits per second. Frequency is less than 6 gigahertz. The latency has been cut down to 10 milliseconds, and the number of antennas that are supported are approximately 4 to 8. If we take one step further, we look at LTE 13 and 14, and we see the data rates have risen to 3 gigabits per second. The frequency is still less than 6 gigahertz, and the MIMO antennas have gone up from 4 to 8 to 8 to 32, and the latency has dropped down to 2 milliseconds. So those are all very good advances in the technology. And then by the time we hit 5G, what I really want to emphasize here is that the data rate now has jumped up to 10 gigabits per second. We're looking at frequencies well above 22 gigahertz. The number of antennas that can be supported jumps all the way up to potentially 256, and the latency is dropped well below 1 millisecond. And that's important for some of the applications that we're going to talk about here in the next couple of slides. So if we take all of the applications that we run over 5G and put them into a triangle, we can start to sort them along these three different axes. And each one of these axes will require a different network topology in order to support it. At the top of the triangle, we have an enhanced mobile broadband, and it's characterized mainly by just the raw amount of data that you can send to a device, all right? So the network that'll be used to support those kind of applications are going to be the high density deployments of the smaller base stations. Is going to use the high frequency signals so that you have the larger bandwidth. When we move down to the bottom right of the triangle, these are applications that are looking for low latency, but also ultra high reliability. And one of the good examples for this type of application is a self-driving car. So you don't want to be in a self-driving car and have the network being dropped in and out. And you definitely don't want a lot of latency because you don't want the car behind you to end up rear-ending you, right? If we move to the left side, the bottom left side of the triangle, this is where we have the massive Internet of Things, or IoT. And this network will be characterized by low frequency, low bandwidth connections, but the ability to support many, many different devices at a single time. Taking this one step further, the infographic that we have on this screen gives you a little bit of idea about the range of each one of these different applications of 5G and what kind of distances you might get or coverage areas that you might get. So in the very center of the infographic, we have the 10 gigabit 5G signals in an urban environment. This is where you'll have high frequency signals and you'll have very high density deployments of the antenna systems. The middle range is the sub-gigahertz frequency range, and this will give you approximately 1 gigabit per second, and it'll be used for things like the self-driving cars, large public gatherings, and to cover a much broader area. The third and outer ring is what we call the ubiquitous LTE, and this is where we get into connecting many, many different devices at a time and being able to connect them efficiently without degrading the network performance. Within this ring is where you'll have the long-term evolution used for IoT. It'll be used for the fixed wireless to residential applications. It can be used to provide entertainment or infotainment options within the automotive sector, and possibly even within the agricultural area as well. So these real-world applications that we'll see, the first one that you're going to see is fixed internet. And we'll talk a little bit more in the next slide. But the idea here is that you'll be able to use 5G to either compete with or replace things like cable internet service providers or other wireless internet service providers. The second one is entertainment. And this is talking about things like 4K and augmented reality, where the raw data rate that you need to support these things can be quite high at times. The third is automotive, which includes vehicle-to-vehicle communications, as well as vehicle-to-devices inside the automobile. IoT is a large set of different sensors and other items that can be connected to the network, but don't really use up a whole lot of bandwidth on the network. And the last is wearable technology. Most people are already familiar with the smartwatches, as well as Fitbits and other devices like that. But really, one other application that we could see here for wearable technology is in the healthcare space. So if you think about all the applications in a hospital, for instance, where you want to monitor the patient's heart rate or blood pressure or whether they've moved around the room or not, there's a great opportunity here for technology to really improve the way that we do healthcare currently. So looking here real quick at the timeline, you can see that in last year, there were limited trials around the country of 4G LTE upgrades and 5G trials. This year, the trials have continued, and we'll see the first large commercial rollouts, which we'll talk about in the next slide or two. And then moving forward to next year, there'll be data center expansions. 4G LTE upgrades will begin to diminish and be replaced with more 5G. And as we move through 2020 and 2021, the number of 5G deployments will continue to expand, roll out across the country, as well as additional data center expansion. And we'll start to see a lot of machine-to-machine data start to flow across the network. By the end of 2021, we expect this to be the end of the initial 5G wave. So you may be thinking, when will I start to see 5G devices? So here's a spattering of some of the equipment that'll be available. Samsung are expected to be in the near future. We don't think it'll be the S10 version. Apple is believed to be intentionally lagging behind everyone else, possibly launching in 2020. We know that the iPhone XS, the Max, and the XR all use gigabit LTE currently. And LG and Motorola are both looking to have devices on the market early next year. LG will be with the Sprint network, and Motorola will be with Verizon. So the first application of 5G that most people will see is this idea of using 5G as fixed internet. And this will mostly impact fiber to the home deployments. So 5G will be more cost effective to deploy than the FTTH. And in fact, just this month, Verizon has started offering fixed wireless for residential services in 4 different cities, with those cities being Houston, Indianapolis, Los Angeles, and Sacramento. And what they're offering is about 300 megabits per second or up to 1 gigabits per second, depending on your location, for either $50 or $70 per month, where the $50 per month is for people who are currently Verizon customers, and the $70 will be for new customers. One interesting thing to note here is that this system will launch with Verizon's proprietary 5G equipment. And in the future, when the 5G is fully standardized and rolled out through the entire network, Verizon will come back and replace the equipment for you at no cost. The way it currently works is that you'll get a base station for your house that communicates with the 5G network and also has Wi-Fi built in, so that you have just one device acting as your router and your wireless access point. We see this as being very beneficial for underserved communities. This would be people who either have very poor internet service currently or no internet service. It'll also be very beneficial for people who have small numbers of choices. Maybe you only have one choice for your internet service provider. Hopefully 5G will be able to offer competitive pricing and will help consumers out in that way. And that will directly compete with cable, DSL, and other types of wireless internet service providers. As far as the enterprise goes, it's unlikely to replace enterprise Wi-Fi in the next 10 years. Part of the reason for that is that the millimeter waves are easily blocked by building materials such as drywall, flooring, carpet, and that's going to require the antenna to be deployed in a more dense fashion than what Wi-Fi is. It's also unlikely that you'll go through and retrofit all the devices in your enterprise with 5G adapters. People simply aren't going to go and change all of the laptops, all of the phones, all the printers, and other devices. And if a business already has fiber running to their enterprise, it's unlikely that they'll switch to 5G. So those are the primary reasons why we do not see 5G replacing Wi-Fi in the enterprise within the next 10 years. The other thing that we see happening is that we think that the 5G experience outside of the workplace will start to drive demand for higher performance in Wi-Fi beyond AX. And if everything holds as it currently does, fixed internet with Wi-Fi will be more cost effective than 5G on a per gigabyte basis. So some final thoughts here. 5G will drive global cellular infrastructure improvements for the next 10 to 15 years. It will offer better service for mobile users, mobile applications, and it will bring more competition for fixed home internet for underserved locations. 5G will not displace Wi-Fi in the enterprise, most likely due to cost. So you can expect better enterprise wireless performance with 802.11ac and AX and beyond.
Great. Thank you, Mike. Now for the final portion of our presentation, we'll pass it back to Una. Una, you have control.
All right, so I would like to wrap up our webinar by saying we need to choose wisely. We cover most of the current enterprise wireless options we have today and emerging options that we know that are coming in the next few years. And this table summarizes those options. Now, we talked about speed, we briefly touched on cost, and we reviewed cabling structuring and design. And based on that, this summary put together, it is evident that considering the speed, reliability of network, and the cost of implementation and use, Wi-Fi 802.11ac or higher combined with Category 6A offers the best solution for enterprise applications seeking system longevity, faster data rates, and support for high bandwidth wireless networks. And remember, it is not just about wireless access points and switches. The design of your network and products that you choose will determine the overall performance of your wireless network. And when making the product choices, we need to carefully evaluate product features and values. Can the product support PoE? Are they Platinum rated for Platinum space installation? Are they third-party tested or do they meet all the standards? So make sure that we're not just choosing products that are out there. We need to choose good products and reliable products. Remember, there's no network that is only wireless. Good wireless network always required a good wire backbone. So Bertech Leviton Technologies provides cabling and connectivity solution, and we have a very strong partnership and alliances with active tier manufacturers. We work very closely with each other to make sure that our products are compatible and interoperable, and we have the right solution for the next generation enterprise wireless deployment. Leviton's Atlas X1 component-rated Cat6a jack and patch cord provide the best-in-class performance, enhanced alien crosstalk protection, and they have been independently tested to guarantee to exceed all components, permanent link, and channel margins. Vertex XTP cable also provides the industry-leading performance and extra margins to support massive data traffic. The unique cable design with the smaller diameter allows for improved density and better operational airflow and cooling, which makes it an ideal solution for PoE support in web installation. We also provide a Platinum-rated web solution that is engineered to support all wireless and PoE demands. To enhance our connectivity installation, we have the quick core installing brackets and surface mount boxes to provide a fixed location for connectors after they're terminated and to reduce potential damage before installation. Again, our entire web system that includes our jacks, cable, patch cords, bracket, and surface mount boxes are Platinum rated per UL 2040, and we are the first manufacturer who provides the end-to-end Platinum rated solution in the market.
It looks like we're close to the end of our time here, so this will conclude our presentation. Any questions we didn't get to live, we'll follow up with offline. On behalf of our presenters today, Una Shin and Mike Good, we thank you for attending Bertech Leviton Technologies webinar.